Okay, well, first of all, thanks to the organizers for organizing this wonderful workshop in Christoph's memory and for inviting me to participate in it. And I'm going to talk about a subject that was already mentioned by Antti in his overview talk at the beginning, which is the subject of spontaneous stochasticity. And so I'm going to try to give an update about our current understanding of this phenomenon. Okay, so the origins lie in this paper of Bernard Gawędzki and Kupiainen. And as you can see in this underlying passage, they pointed out this indeterministic behavior of Lagrangian trajectories at high Reynolds number in turbulent flows. And this was an idea that it was clear Christoph was particularly enamored of, and he mentioned it and advertised this notion in several lectures. I know at least 4 in which he spoke about this phenomenon and emphasized its importance. And so I'm going to try to explain some of our modern understanding of this. But first of all, let me just review what they did in this very first paper. They were considering a phenomenon of breakdown of uniqueness of the initial value problem for ordinary differential equations. So we all know that if you have a velocity field satisfying a Holder-Lipschitz type condition when h is equal to 1, then there's a unique solution of the Cauchy initial value problem. However, if the velocity field is merely Holder continuous with h less than 1, then there are generally a continuous infinity of solutions of the initial value problem. This is something that we all learn in our first fundamental course in differential equations. Then the idea is that Ansager pointed out that in a turbulent flow, already in 1949, that to explain experiments on the observed dissipation of kinetic energy, the Holder exponent of the velocity field has to be less than 1/3. And so the question is, how are the little parcels of fluid, the Lagrangian particles in the turbulent flow, affected by that roughness of the velocity field? Okay, so a lot of our understanding of this can come already from a very simple toy problem. And this is the basic example of non-uniqueness. It's given in every elementary differential equations book, where you just look at dr dt equals r to some power, where the power is less than 1. And here we can think of that as a very simple toy problem for the separation or the growth of separation of a pair of particles. So here that's what I've indicated is those 2 particles here. Let's see, where's my clicker? So here I have particle 1, particle 2, and I just look at the distance between them. And so I simplify the whole turbulent flow by just assuming a Kolmogorov power 1/3. It's easy to solve this by separation of variables. You can see the solution. The important point is that at sufficiently long times, much longer than this time that depends on the particular initial separation here, you just separate like a t³ power, and the initial separation is forgotten after that time. But correspondingly, you can take the limit where the initial separation goes to 0. You take the infinite Reynolds number limit first, then you let the separation go to 0, and then you still separate to a positive distance in any positive time. So that means that you have 2 particles starting at the same point that end up in different places. Okay, so this is in fact something that has been known a long time in the turbulence literature, going back to the work of Louis Fry Richardson in 1926, who studied this phenomenologically, experimentally, in particular with phenomena like spreading of ash plumes, smoke plumes, balloons in the atmosphere. He looked at a wide variety of data, and he saw exactly this Tcube behavior, the so-called Richardson Tcube Law. But we see it now more precisely in numerical simulations. Here's very nice work of Battani et al. So this was Jeremy Beck and his collaborators. This is already about 10 years ago, where they looked at a fully developed turbulent simulation, pseudospectral calculation in a periodic box. And they put particles into the flow with different separations. And so these different curves are starting off the particles here at different initial separations, at 2 different Reynolds number. And what you can see is the initial separation is decreased. The particles still bend over to the same curve at long times. And that's the Tcube law that was predicted by Richardson. And so just like in the little toy problem, the particles forget their initial separation at sufficiently long time. I should say that these effects are still not unambiguously seen in laboratory experiment. It's very, very challenging to do this because there's a big difficulty in tracking particles experimentally that are starting very close together, which means you have to densely seed the flow and then evolve a long time. But our best evidence for that this is real comes from numerical simulations like these. Okay, so now let's go back to the work of Bernard et al. And the problem that they studied was essentially that of a dimolecule. So you put a little molecule into your turbulent flow, and now it's subjected to two things. It's subjected to physical Brownian motion and also to turbulent advection. And so you model that simply with this Langevin equation, where this is the turbulent velocity coming from the Navier-Stokes equation, for example, with a given viscosity. And then you also have here the molecular diffusivity of the particle, the little dye molecule. And so what they argued is that if you consider this problem in the joint limit where diffusivity and viscosity both tend to zero together, or more physically, we should say the Reynolds number gets large and the Peclet number gets large together, then these particles, this particle distribution given by this Feynman-Katz representation, this path integral representation, although naively, looking at it, you expect it will shrink to a delta function on the unique solution of the initial value problem. Because of this non-uniqueness phenomenon, it does not go to a delta function, but to a non-trivial distribution, and thus there is a breakdown of usual Laplacian determinism. You actually end up on a nice distribution over the set of non-unique solutions of this ordinary differential equation. Okay, so here's a little simple picture that I hope sort of brings these ideas very clear. The top curve represents what would happen in a laminar flow if I take this joint limit of diffusivity and viscosity going to zero. In that case, the laminar flow just converges to a smooth solution of the Euler equation, and all of these trajectories collapse onto that nice, unique trajectory. I'm not pointing anymore, but anyways. I think I burned out the pointer. Okay, so anyways, you collapse onto this nice, unique trajectory. But in the turbulent case, where the limiting solution has many non-unique trajectories, so there are many non-unique solutions of the initial value problem, in this limit, you don't collapse to something that's a single thing. You go to a distribution on these non-unique solutions. Okay, so there's actually a very close analogy to zero temperature phase transitions in certain problems in equilibrium statistical mechanics, where there are non-unique ground states. And here, the analog of the energy of the Hamiltonian system, of the statistical mechanical system, is the action that appeared in that earlier path integral, and those non-unique solutions are the exact analog of ground states. Okay, so the first use of the term spontaneous stochasticity seems to be in this review by Grisha, Christoph, and Massimo, and we're lucky we have, oh, thank you. We're lucky we have Grisha and Massimo both here. So this seems to be the first place where this term, spontaneous stochasticity, was used for the phenomenon, where they said that it seems to constitute an important aspect of developed turbulence. Okay, so the notion of spontaneous, of course, arises from analogy with similar problems in statistical physics, like spontaneous magnetization, where you let the external magnetic field go to zero and you have a remnant magnetization, spontaneous magnetization. Here, you let the external noise source go to zero and you have remnant stochasticity. And so that's sort of the origin of this terminology. Okay, now what they further pointed out in this paper is not only does this happen, but it's fundamentally important to explain observations. In particular, it's well known, there are many experiments that show that in this joint limit of high Reynolds number and high Peclet number, the mixing of the scalar is unaffected. the scalar continues to mix, even though the molecular mixing is getting very small. In fact, we all have day-to-day experience of this, because if your significant other walks into the room, you smell their perfume or cologne, even though with a heavy aromatic molecule, it would take months for the perfume to diffuse over scales of tens of meters. And the reason that we smell it as quickly as we do is because there are speakers waving their arms around and fans blowing and vents that are creating little small-scale turbulence in the room, and that's why we can smell it, not because of molecular diffusivity. And so they said that in order to understand this rapid mixing rate, this effect of spontaneous stochasticity is fundamental. And you easily understand it by writing a Feynman-Katz representation of the corresponding advection diffusion equation. Oops, I'm now going forward. So oh, I have to go backwards, sorry. Yeah, so of the advection diffusion equation here. Now I'm not doing that one. I must be doing this wrong. Okay, it's probably not broken. I'm just not doing it right. Pardon? That is the pointer. Now I must be doing this wrong. Let's forget about the pointer. Okay. So the point is that you take that advection diffusion equation and you solve it with a Feynman-Katz representation in terms of that same path integral, in terms of this transition probability, but now for backward in time. So you're going to start off at the position of interest, x at time t, and go back to the initial data, and this gives the exact path integral representation of the solution of that advection diffusion equation. And then the point is that in this joint limit of nu and d going to 0 together, you can pass to that limit, and precisely when this thing is not a delta function, you get a non-trivial average over the initial data. And then, as they pointed out in their paper, if you look at a measure of mixing, such as the scalar intensity, the intensity of the fluctuations, in the long time limit, when everything is missed, all these fluctuations die out and it goes to 0. But this is a nice convex function. So simply by Jensen's inequality, you can see that having this non-trivial average is going to produce a monotonic decay in this quantity. And that's their explanation for the origin of the turbulent dissipation of the scalar contaminant. Okay, so they worked originally in the context of the Kriknen model, although this argument is actually very general. They worked originally on the context of the Kriknen model, and there was many works following on this. Antti already mentioned the following work of Christoph and Massimo on the compressible case, and there was related work to that by Wayne and Eric van den Einden. All of these works were made fully mathematically rigorous by work of Lejeune and Ramon using methods of Wiener chaos expansions. And so this is now sort of the classical part, and it's generally well understood, and all of the picture that they had proposed is fully confirmed in this case. We know there's spontaneous stochasticity in this Kriknen model, which is the delta correlated in time Gaussian velocity field case. So I should have said that at the beginning. But this picture goes far beyond the Kriknen model. Already in later work, 2003, Chavez, Gawędzki, Horvath, Kupiainen, and Vergasola generalized some of these results to more general problems of Gaussian ensembles, so not delta correlated in time. It was also extended by myself, I think for the first time, to nonlinear advection. So none of this depends on having linear equations, and using work of Peter Constantin and his student Gautamir, who showed that essentially the Feynman-Katz representation also holds for classes of nonlinear equations, including Berger's equation and incompressible Navier-Stokes. We showed that spontaneous stochasticity occurs in the Berger's equation, and it's also responsible there for the dissipative anomaly in the Berger's case. But more generally, the argument of Gawędzki and Kupiainen that I sketched has nothing to do with white noise advection. And in fact, with essentially just adding a few epsilons and deltas, their original argument can be made into a fully rigorous proof. And it can also be extended to other situations with external forcing by using some additional tricks. And I discussed this with my student Theo Drivas, where we showed that whether it's passive or active advection, as long as you're away from walls, the only way that you can get anomalous dissipation of the scalar is by this effect of spontaneous stochasticity, Lagrangian spontaneous stochasticity. It's the only game in town. And if the scalar is passive, then it's also sufficient. Okay, so it's really a very, very general and unique explanation of the experiments on scalar dissipation. But in fact, it's far more general than that. I already mentioned that this Feynman-Katz type representation can be extended also to nonlinear systems, including Navier-Stokes. Here is a work in which we considered MHD, nonlinear MHD, in a turbulent case, and the work of Constantine Ear can be extended there, and it describes the transport of magnetic fields in nonlinear MHD. I'm not going to go into the details of this, but essentially the magnetic field lines are transported essentially like passive scalars along the trajectories of the backward in time Brownian motions. The only additional fact is that because they're magnetic field, because these magnetic fields are vectors, they also have to be rotated suitably as they go along those trajectories. And then when you get to the final point, you average over all possible trajectories coming into that point at that given time, and that gives you the resultant magnetic field. Now, the usual lore in MHD is that in the limit of very high conductivity, you will get standard flux freezing, which means there's just one trajectory, and all the magnetic fields are just brought in along that line in a frozen way. But what we found is the numerical evidence in this paper, which is that that's not true. And in fact, you see exactly the same Richardson phenomenon backward in time. And so in the limit of high conductivity, standard flux freezing is completely broken in the usual sense, but it remains as a stochastic phenomenon. And then we argued that this accounts for fast magnetic reconnection in turbulent MHD plasmas in astrophysics. And also, you can extend this even to quantum fluctuations. So going back to our earlier discussion in the prior talk about quantum effects, in another work with Theo, we found that quantum fluctuations in models like that toy problem of ODEs are sufficient to trigger spontaneous stochasticity in the semi-classical limit. So you can completely defeat standard spreading of the wave packet. All the usual things that you learn in the textbooks are totally wrong. You can take a massive particle, the mass of the galaxy, and what will happen is that instead of following one unique classical trajectory, it will stay random and it will follow the multiple trajectories of the limiting singular dynamics. If you take a limit jointly where the particle becomes very, very massive, and simultaneously the potential in which it moves becomes more and more singular. Okay, so this is a phenomenon that goes far beyond hydrodynamic turbulence and presumably appears in many other systems. Okay, so one of these is the case of Eulerian spontaneous stochasticity. So just to give you the setting for this, I want to show that all the ingredients are present here. If you consider a simple situation like a mixing layer, a Kelvin-Helmholtz unstable mixing layer, velocity on one side moving to the left, on the top, on the bottom moving to the right. You consider this as an initial singular vortex sheet. Then it was proved a long time ago by Andrew Maida that for systems like this with vortex sheets of a distinguished sign, there are weak Euler solutions that you obtain in the infinite Reynolds-number limit. But from later work using convex integration methods, this was done by Laszlo Szekelyhidi about 10 years ago, there is more than one Euler solution for that set of initial data. In fact, there's a continuous infinity many of such Euler solutions. Okay, so this provides the same ingredients as we found for the Lagrangian particle case, but now in the Eulerian setting. And so this was the motivation of the work of these gentlemen, Dalibard, Beck, and Mailybaev, where they showed that the same effect, the same phenomenon also happens for Eulerian flows. And what's being shown here on the right is this dispersion in the L2 norm. So you're just looking at the velocity field and then measured by this norm here, this energy norm, that equation down below. And they're plotting this for cases where you're decreasing the viscosity, So you have a viscosity, and you also add in small amplitude noise. And the viscosity and the small amplitude noise are going to zero together. And what they find is that you get this dispersion effect, very much like the Richardson dispersion for the Lagrangian particles, so that at long times, all those situations bend over to that same curve, even in the limit where the noise is vanishing and simultaneously the flow is approaching more the Euler limit. Okay, so this is what they referred to as Eulerian spontaneous stochasticity. And this is actually based on earlier work of Mailybaev on shell models, where he proposed the same idea. This was already about 5 years earlier. Okay, so here we have empirical evidence, at least, and some theoretical understanding that the same thing could happen in the Eulerian framework. Now, if you think about this, here they're taking very little tiny perturbations, and the classical idea in much of the geophysics literature is this is like the flap of a butterfly wing, little copepods swimming in the ocean, some small little perturbation. But you can ask yourself the question, what about thermal noise? Because thermal noise is inevitable. We know that the validity of a hydrodynamic description depends explicitly on having local equilibrium. And in a local equilibrium of the fluid, thermal fluctuations are inevitable. Okay, so this is a question that I now want to try to answer. This is recent work that I've been doing with my colleagues that I had listed at the beginning of the talk, Dima Bandek, Nigel Goldenfeld, and Alexei Mailybaev. And so we asked the question, well, what about the effects of thermal noise? Well, we know how to model that. There's been a lot of successful modeling of thermal noise, mainly for laminar flows, very far from equilibrium, but mainly laminar. And so we have good confidence that we know how to do this. We just use the Landau-Lifshitz fluctuating hydrodynamic equations, which here I have written in the incompressible fluid form, so the low Mach number limit. I will want to stress that for mathematicians in the audience, although this looks like a continuum stochastic PDE, which is horribly ill-defined, every physicist says that's not a physical way to interpret these equations. You have to put a high wave number cutoff. So in the language of physics, these are low wave number effective theories. You are not supposed to take this cutoff going to infinity so that you have a continuum description. And indeed, you can put this cutoff pretty much arbitrarily where you would like between the so-called gradient length, which in a turbulent flow is the Kolmogorov length scale, and a scale of the order of the mean free path, as long as you suitably adjust the viscosity to correspond to that cutoff. So the viscosity that appears here also depends on that cutoff. There's a renormalization effect coming from changing that cutoff. Okay, so we're going to take this equation and we say, okay, now let's non-dimensionalize it. We'll use standard inertial range scaling with the integral length and the RMS velocity. This is what pops out. You get the dimensionless groups. The standard one is the Reynolds number, but this term breaks standard hydrodynamic similarity. The Reynolds number is not the only dimensionless parameter, the only dimensionless number group. You also have this parameter theta k, which is physically the thermal energy relative to the energy of a Kolmogorov scale eddy. And then you have the other dimensionless parameter, which is giving you the forcing. This is related to the so-called Grashof number. And then you also have this dimensionless cutoff, which, according to the description I said before, lies between two limits, both of which go to infinity as the Reynolds number goes to infinity. So Kolmogorov is Reynolds to the 3/4. If I go all the way down to the mean free path, it's Reynolds number to the first power and divided by Mach number. Okay, so in this description, the thermal noise is very small, even at the Kolmogorov scale. So here, that theta k in typical flows is something like 10 to the minus 8. So it's really, really tiny. But we would like to ask the question, can this have some indirect effect in the inertial range? And to prime this, the similar question we know is true experimentally, that even though that Reynolds number term is very small, energy is still dissipated experimentally. We observe this in many turbulent flows in the infinite Reynolds number limit. So even though that Reynolds number term disappears and you get Euler equations formally in the limit, nevertheless, those limiting Euler solutions are not your father's Euler solutions. They're not smooth. They're singular Euler solutions that dissipate energy. And so the question is, can you have a similar effect coming from the thermal noise? Okay, so we can try to address this by looking at the path integral representation, just like we did for the Lagrangian motion of the particles. Here I've written out this path integral description. It's in terms of the so-called Onsager-Markup action. I'll just mention that this action has been rigorously derived for stochastic particle models by Quastel and Yao a long time ago in a very nice paper in Annals of Mathematics, but in the wrong limit physically. They're looking at sort of a standard scaling limit, and this standard scaling limit is assuming some hydrodynamic similarity, which in general for real thermal noise is broken. And as we discussed at length in an earlier paper, the limit that they consider is unrealistic physically. It's never attained anywhere in nature, probably, for a molecular gas. If you wanted this limit to be valid, you would have to take lambda incredibly so small. I mean, we can go into that in more detail, but it's not a physical limit that they were considering for molecular systems. But anyways, we can take the path integral representation, and now we can say, what can we guess from that? Well, if you did the naive thing, you would just do a Laplace approximation, and you would say, okay, I believe that I'm going to get a large deviations type result, a law of large numbers, and I'm going to, at very high Reynolds number, I will see the unique solution of the forced Euler equation. However, we know quite in general for these types of weak solutions that they're not unique. There's been a lot of work on that in the last, 15, 20 years. I think I first learned about this work, in fact, from Jan Ver on a visit back to my own home in Arizona. And it's now been highly developed. And one of the essential conclusions of this work on convex integration is that these kinds of weak Euler solutions, even if they are dissipative and Holder continuous, are not unique. In particular, there is generally a dense set of initial data for which you have infinitely many solutions of the Cauchy initial value problem. Okay, so again, we're in this setting where you can have spontaneous stochasticity also in the Eulerian setting. Okay, so what I'm going to present here first are some numerical studies of this. We're just finally getting ready to submit this work. We've been working on this for a while. Fine-tuning all the details. Nobody can reach the high Reynolds numbers required here with simulations of the Landau-Lifshitz equations. I mean, the current state of the art is that they can get a Reynolds number about 500 or so. We need to go considerably higher than that. And so we're going to resort to so-called shell models, which are little simple toy surrogates of the Navier-Stokes equation. We now add to the standard shell model a representation of thermal noise. So for people that were familiar with that earlier paper, we're not going to use the same noise. That noise was chosen so that we created detailed balance at high wave number and equipartition at small scales, and that was appropriate for our study of the dissipation range. But here we chose a different noise with a different spectrum, and it's particularly that eta term there, the white noise term. We have a scaling there, kn cubed. And that's chosen so that we get the same Reynolds number dependence as for 3D Navier-Stokes. It turns out that also produces a k-squared spectrum at high wave number, which for 3D would be equipartition. In the zero-dimensional case of the shell models, it's not. But we chose this so now nobody can accuse us of using a noise which is too strong. So the other noise that we used in the earlier paper is actually much stronger at low wave numbers. This choice of noise has the same strength as for Navier-Stokes. By the way, we're putting our hands behind our back because in Navier-Stokes, that same noise acts on many, many Fourier modes. Okay, so we're saying, okay, no, we're going to take that size of noise, but act just on one mode, because that's all we have at high wave number. Every shell has one mode. And so now we study numerically this limit of letting the Reynolds number go to infinity. Okay, so the general expectation is that in the infinite Reynolds number limit, both of these terms are going to vanish. And in fact, there's rigorous studies of this, not for the stochastic model, But for the deterministic case, where Constantine et al. Proved that if you take the zero viscosity limit of these models, you do get weak solutions of the inviscid equations. I actually have a student working on this problem at the moment for the stochastic case. But in any case, so here are some numerical results. So first of all, we look at the L2 error growth, and that quantity is defined down at the bottom. The averages are all here over realizations of the thermal noise. Okay, so all these, we're starting off with one fixed initial condition. The initial data is that solution up at the top. It's this 1/3 power law solution, K41. It's an exact, unstable, an exact steady state solution of the inviscid shell model, but unstable. And so now we're perturbing it with our thermal noise, and we study the growth of the variance of this ensemble of solutions of that stochastically perturbed system. And there is the variance growth in time. And over on the right, we have the detailed spectrum. That is, before we sum over n, it's each one of those individual variances of all the shells plotted as a function of time. So the three different colored curves are three different times. So you can see how the variance is progressing to larger scales. Okay, now all of these features can be understood from classical work of David Ruel and Edward Lorenz. Okay, so I just will briefly remind you that Ruel wrote a paper in 1979 considering the effect of thermal noise on a turbulent flow, and he pointed out that in essentially one Kolmogorov time, thermal noise will reach the Kolmogorov length scale. And I'll just say that his estimate here is exactly related to this parameter that I called theta k, which is this the thermal energy relative to the Kolmogorov scale eddy. And so this parameter is very small, theta k, but since it's appearing inside a logarithm, a logarithm cuts anything down to size. And so in just a few Kolmogorov times, the thermal noise affects the Kolmogorov scale eddies. Even earlier, in the work of Lorenz in 1969, he had pointed out that any small-scale disturbance, he wasn't thinking of thermal noise, but of things like little microorganisms or little fish swimming in the ocean or little butterflies in the atmosphere, would create small-scale perturbations that would propagate up to the large scales. And said already then, it is proposed that certain formally deterministic fluid systems which possess many scales of motion are observationally indistinguishable from indeterministic systems. Specifically, the two states of the system, differing initially by a small observation error, will evolve into two states differing as greatly as randomly chosen states of the system within a finite time interval. So unlike chaos, for which Lorenz is also regarded as a pioneer and founder, he was saying this is more than chaos. That, if you take the noise getting smaller and smaller in a chaotic system, the horizon of predictability grows and grows and grows. You can predict longer and longer and longer. He's saying, no, not for systems of this type. Here, when you let the noise go to zero, the predictability horizon does not increase. You stay unpredictable. Okay, so he cannot be lengthened by reducing the amplitude of the initial error. Okay, so this is exactly explaining what we're seeing here. Because we have thermal noise, we see an initial linear diffusive growth. That's just the direct effect of the noise. Then we go into the Ruel exponential. So there's an exponential fit to that early time. And then at long time, we go to this Lorenz prediction. This was later studied by Craikson and Leith, who pointed out in particular that this should be a linear growth, epsilon t. And that's exactly what we see in this problem. And then on the right, this is exactly the error spectrum picture that Lorenz proposed in his 1969 paper. So, in fact, what we're seeing here on the right is virtually lifted directly from the work of Lorenz, who obtained the same result from a closure calculation for a 2D Euler system. Okay, so I should say all the simulations that I'm showing here were performed with the flow parameters of the atmospheric boundary layer. Okay, so in particular at scales of a few hundred meters and in one large eddy timer. So if you go, say, about maybe even up to the largest scales of the 3D atmospheric boundary layer, which could extend up to maybe a kilometer, or at least a few hundred meters, the molecular noise will reach those scales in a few eddy turnover times of that scale. Okay, so just a few eddy turnover times of that scale, you will see the effects of thermal noise and the randomness, the resulting randomness. So not just the flap of a seagull's wing or a butterfly, even the molecular agitation is sufficient for this. Okay, now what's really crucial here is the dependence on the Reynolds number. And so here I'm showing several measures of that. One question we can ask is, how long does it take to randomize? I just said it takes a few eddy turnover times. This plot on the left is the demonstration of that. We define the randomization time as the time that it takes for the variance to reach the level of the energy of any given mode. And so then we plot those randomization times versus the shell number. And what you see is that as you go into the inertial range to larger and larger cells, that's larger and larger length, smaller and smaller shell numbers, larger and larger length scales, you turn over and this randomization time approaches a multiple of the local eddy turnover time. In fact, it's about 3.4 for this toy problem. Okay, so in about 3.4 eddy turnover times inside the inertial range, you feel the effects of the thermal noise. And then here we have the analog of the Richardson plot. So what we're showing on the right is what happens as we simultaneously decrease the noise and the viscosity by simply increasing the Reynolds number with all other parameters fixed. And you see that just like in the Richardson case, as you decrease the noise, you bend over to the same curve, and in the limit, you don't know what the strength of the noise was. You could take it to 0, and it stays random. Okay, so this is, again, a fundamental indicator of spontaneous stochasticity. But here's the smoking gun. Okay, we sit at a given shell number inside the inertial range, and we simply raise the Reynolds number. And so these plots are looking at simple statistics in the inertial range. For example, the modulus of one of those complex modes, or the energy flux, the transfer rate. All these quantities are local in scale quantities, standard things to look in the turbulence literature. And we vary the Reynolds number here by about 2 orders of magnitude. And what we see is that the statistics in the inertial range coming from the thermal noise, no other source, we're starting off with a deterministic K41 solution, they become independent of the noise, and we go to some statistics that don't depend on the noise strength at all. So this is the really clear signature of spontaneous stochasticity in the limit. And so again, I'll recall the statement of Lorenz that certain formally deterministic fluid systems will be operationally indistinguishable from indeterministic systems. By the way, how much time do I have left? How much? 10 minutes, okay. In that case, let me say in the last 10 minutes a little bit about theory. Okay, so a lot of the things that I just told you about come from numerical simulations, and I should say that all of the understanding of spontaneous stochasticity that we have mathematically so far comes from very special systems, things like the Kriknen model, the general argument of Gawędzki and Kupiainen applies in general, but we can't prove for real systems that there is an anomalous dissipation of the scalar intensity. So if you assume that that's true, then spontaneous stochasticity follows from their argument. But the only models where we really understand these and their connection are in a few scattered models. And so one of the things we would like to do is get a more general understanding. And so let me say a little bit about RG descriptions of this. Okay, so first of all, why is RG even a good idea here? If you think about it, it's very natural because the basic effect is your forgetting of the initial data. And this is exactly analogous what happens in critical phenomenon, where when you start off at the lattice scale, you have the details of the microscopic Hamiltonian. But when you go to larger and larger scales, all those details are washed out, and what you see is some universal limit governed by the fixed point of the renormalization group. Okay, so the same idea should also be applicable here, now thinking of terms of the forgetting of the initial data, the precise initial data. So we looked here at the simplest toy problem. It's been very much studied in the probability literature, especially by Flandoli and also others. And we've generalized it somewhat because one thing, to make this physical, we want to make the velocity smooth. We don't want to consider the limit of infinite Reynolds number. That's never physically achievable. All the effects we're talking about should happen for large but finite Reynolds numbers. And so we take the velocity field and we smooth it. It doesn't matter particularly how we do it. Here we just put that thing in the denominator to smooth out this singularity at the origin. And then we add in the noise, which represents the Brownian motion. So you can think of this as the simplest toy problem of turbulent advection by a singular velocity, but there's just a singularity at one point at the origin. And so we know that the singular deterministic dynamics has infinitely many solutions. Here they're calculable, they're well known. And what we see now is that first of all, when you study this numerically, which we've done both theory and the numerics of this, you see exactly the Richardson phenomenon, that again, the system forgets the level of the noise. As long as you take those to zero together, and it doesn't matter really how you take that ratio, but you fix the ratio, you let it go to zero together, then the system forgets that noise, forgets the precise noise level at long times, and at long enough times, and you go over to a universal statistical behavior. So this suggests that what you should do for these problems is integrate out the early times. Now, for people that are thinking about solving an initial value problem, this sounds crazy. Why would anybody solve an initial value problem by integrating out the early times? That sounds crazy. You want to match the initial data, right? But these are not standard initial value problems, and precisely you want to integrate out the initial value because the precise initial data don't matter. There's a whole wide class of initial data that in this limit all go to a delta distribution. They all start off at that origin, but they all exhibit the same long time behavior. So your RG should in fact be integrating out the early times and then rescaling so that you get an effective initial data, which is the long time attractor. That's the intuition about applying RG to this problem. Okay, so this is what I say here. Okay, so it's easy to implement it in this model in particular because this model is Markovian. It's a simple Markov process. So you have a Fokker-Planck equation. And when you implement the RG strategy that I just described, you get simple partial differential equations which describe the RG flow. And it turns out you can easily analyze this. We have full control of it because you can use orthogonal eigenfunction expansions and you can do everything analytically. And we can sort of exhaustively study this problem using a renormalization group. And I should say, unify all the previous results that I'm aware of in this problem and extend them. So we can describe the so-called singular large deviations. You don't get standard Frodlin-Wenzel large deviations in this zero noise limit unless you start away from that point at the origin. And if you start at that origin, you get a new singular large deviations. And that's described as the approach to the fixed point in this renormalization group that we've developed. But we can also completely classify all the fixed points and completely classify all their domains of attraction. So we have a very complete understanding, in this case, of the spontaneous stochasticity from a framework which we hope will extend then to more general problems. So we want to try to go beyond the piecemeal discussion of specific systems and try to get some more general understanding. Okay, so one also can try to develop an RG theory of Eulerian spontaneous stochasticity, and this is the work of my collaborator Mailybaev with Rebecca. So they have made a toy model of a toy model. So the shell models for which I presented numerical results are still too difficult to study analytically. And they said, let's make a model of the same type, but where we now also discretize time, and now we have maps instead of differential equations. And to make them amenable to RG analysis, they build them in a hierarchical fashion. And so this is a picture of the space-time flow of these maps. At the bottom, I give the analytical description. They're simply discrete time maps. But notice as you go down to smaller and smaller length scales, the time steps get shorter and shorter. And this mimics what we know in the turbulent case is that the small scales evolve faster. They've got faster eddy turnover times. And so you have all the ingredients in this model of spontaneous stochasticity. Okay, now the key concept here that turns out to be useful for their RG approach is this so-called half-time flow map, and I indicate that by that green box. And so that's the map that takes you from the initial data to the half-time 0.5. And you'll notice that that particular map doesn't depend on the forcing at the large scale. So those B's at the top represent the large scale forcing. The model has been truncated, in this case at wave number 4. You can put that truncation level anywhere you like. That's the analog of viscosity in the model. Okay? And so now the question is, can you analyze these models and study spontaneous stochasticity? And they've succeeded in constructing an RG transformation here. Let me just describe it for you very briefly. It's given in terms of refinement from one scale to another scale. So here I show you the system with 4 levels and then the system with 5. If you look at the half-time map for the first case, you'll see that in the second case, that's repeated twice here. And then if you simply compose those two half-time maps, you almost have the half-time map of the refined system if you simply add that part at the top in magenta. And so this leads to this renormalization group transformation that they regard, now they can define as a flow on the set of theories on the infinite lattice. Okay, so you can extend this because you have all you could just add zeros below this smallest scale. And then you can regard these as dynamics on the infinite lattice. And what this RG transformation does is it adds another layer and adds another scale of refinement. So in that sense, it's very, very similar to the convex integration studies that are being pursued in the partial differential equations literature. And I also want to compare, as they do, this map with the Feigenbaum map. So it has a very, very similar structure. You're taking the composition of these two half-time maps together with shifts. Of course, you see the scale of those little ones has to be adjusted so that it's the same as that one. So you shift up, sigma plus, you apply the map twice, you hit it with sigma minus to put it back down, and then you add that psi that depends on the magenta stuff. And this is their RG flow map, and what they show here is that indeed there is spontaneous stochasticity. They can prove that there is Eulerian spontaneous stochasticity in models of this class. Sometimes robust and independent of the noise, sometimes dependent on the noise, but it all comes from analyzing the fixed points of this map and their domains of attraction. Okay, so now we have the start of some renormalization group theories, both of the Eulerian and the Lagrangian cases of spontaneous stochasticity. Okay, so let me just say very quickly, I think so the answer to the question, how far do we understand this? I would say in many respects, we're still at the very beginning. Or not quite. We've gone a little further than the very beginning. The very beginning was those guys. We made a little progress, but there's still a lot to do. We don't have general understanding of when this happens. We don't have general tools to understand it. There's still a lot of work that's needed on model problems. There's still work that's needed to be done to connect this with the mathematics of the Euler equation, in particular on the work on convex integration and the Nash non-rigidity and the H principle. We need to make better connections with weather and climate modeling, the work of Hasselmann and others on adding stochastic noise into climate models. There are obvious connections with statistical mechanics, in particular for things like the Sherrington-Kirkpatrick model, where we know that there are infinitely many ground states. And there's hopefully a role for experiment as well. In particular, experimentalists now can do very, very refined measurements, 3D, holographic PIV, and they can give us at some resolution real experimental snapshots of flows, and we can pose the question, are these initial data spontaneously stochastic or not? Okay, this is within the realm of possibility experimentally. So just like we studied the K41 initial data, we can study maybe real experimental data. Okay, so I lastly just want to finish my talk. Many people began their talk with a personal reminiscence. I'm going to end mine. So in some ways, I think the work of Christoph has loomed over my whole career. I began in constructive field theory at sort of at the tail end of the activity there. I first met Antti at Harvard in 1985, but I did not meet Christoph until more than a decade later. It was actually the program on turbulence at IHS in 1997. And I had been working on the problem of scalar dissipation in the Kraichman model. And I went there and I discussed it with Christoph, and I immediately realized he knew a hell of a lot more about this and understood it much more deeply than I did. And he told me about the work that they were doing on spontaneous stochasticity, and I immediately realized that I had completely missed the boat and that they had seen something really fundamental. And I can still remember Christoph's explanation that in the zero noise infinite Reynolds number limit, the solutions would receive what he called an essentially uniform distribution over the set of non-unique solutions. So I'm happy to say I think that Christoph's idea is still alive and flourishing, and this is my snapshot of where we are in understanding it. So thank you.
I want to raise some doubts. And the doubts are that really you want limits. Ask Sergio, for example, to do an experiment when the Rayleigh and Peclet go to some limit at the same time. He can't. He has a fluid that has some Peclet. So, you know, it's not easy to do these limits that you say in reality. Also, another thing that we also always have to remember and we forget, when Reynolds number goes to infinity, the equations that you use lose their validity. We have the compressibility, we have hypersonic booms, we have bubbles, we have all kinds of junk that is going to destroy everything that you say before you go to the right limit. What do we do about it?
Okay, those are really good questions. I have really good answers. Okay, so first of all, I agree completely. But the important point is that these are very similar to zero temperature phase transitions, like in quantum phase transitions, where you don't have to go to zero temperature to see the effect. And this is something that I studied very carefully. We can analyze this completely with our RG theory. And if you look at the phase diagram of Reynolds and Peclet, most of the phase space is the spontaneous statistics. You don't have to go to extreme limits to see it. Now, let me say something about the experiments. So in fact, the reason for not seeing this in experiment has nothing to do with the Reynolds number. In fact, in 2011, I did the problem of taking our Hopkins turbulence database and putting in little stochastic trajectories, and I was astounded and amazed to see beautiful Richardson and beautiful spontaneous stochasticity. Everything bent over and became independent of the noise at Taylor scale Reynolds number of 400, whereas Eberhard Bodenschatz had published a paper in Science saying that at double the Reynolds number, they don't see it. And I think what happens is clear from what I showed you with this numerical simulation of Battani et al. It has nothing to do with the size of the Reynolds number. It's just technical limitations on what they can measure. The essential problem is that the only way they can get good statistics for having many particles close together near the Kolmogorov scale, like Battani et al. Do, is by densely seeding the flow. And then you have to follow them over a long enough time. It's impossible. It totally overwhelms their particle tracking. And so I think it's clear from the work of Battani that et al. And others after that, you don't have to go to these excessively high Reynolds numbers to see these effects. But to see them experimentally is still an extremely challenging problem. And I agree, it's really worth pursuing that and finally seeing it. But I personally don't have any doubt that you see it already at Reynolds numbers that are achievable. It's just the technical, question of measuring it. And then as far as the other effects, I fully agree. But all of these things should also happen in compressible turbulence. They should also happen in relativistic turbulence. They should happen in kinetic plasma turbulence. In fact, because the equation for a plasma, the Vlasov equation, or Vlasov-Landau if you add the collision term in, are scalar equations for the distribution function. And there's a huge literature on the anomalous dissipation of kinetic entropy in kinetic plasmas, going back to work of John Kromis in the 1970s and 80s. Okay, so the theorem of Gawędzki and Kupiainen applies there. The only way that you can get that effect, and there's experimental evidence for that in the magnetosphere, the only way that you can get this is by spontaneous stochasticity of the characteristics of that equation, which are now the Hamiltonian equations of a charged particle. So in fact, you're right, but it goes the other way. This is much, much more general than incompressible fluids. And it should also be true for world lines in relativistic fluid mechanics. So thank you, Itamar, for pointing out the generality of the phenomenon.
Is it working? Yes. So Laure Saint-Raymond is asking, so I had pretty much the same questions. What kind of connection with convex integration do you expect? It is not clear that convex integration catches the whole set of the weak solution.
Well, in fact, I don't personally believe that any of the convex integration constructions are physical. And I think that, for example, there are many, many other properties of Navier-Stokes equations besides energy. They also, the Euler equations, have helicity. They have Kelvin theorems, at least in this classical smooth case. And one of the things that was discovered by Constantine and Eyer in their work is that the Navier-Stokes equation has a Kelvin theorem. And that Kelvin theorem is actually a martingale. It's a backward martingale in time. So if you want to tell a probabilist what is the incompressible Navier-Stokes equation, it's the unique space-time velocity field, incompressible, for which circulations advected by the stochastic particles, adding the viscosity as a Brownian motion, is the unique one for which all these circulations are martingales backward in time. So this property very plausibly extends to the zero viscosity limit. It's the exact analog of the martingales that are found for the passive scalar in the Kupiainen model, where the passive scalar is conserved along the backward trajectories, but now not deterministically, but only as a backward martingale. And so all of those kinds of properties are completely missing in the convex integration studies. However, what they do show clearly, unequivocally, is that if you include Holder continuity, and now they've gone up, not quite to the, well, it depends on the precise statement, but for global solutions, they've gone up to the Holder 1/3. That's this more recent work of Seclidi and Daneri and others. And with Holder 1/3 and dissipative, globally dissipative, there are non-unique solutions. There is a dense set of initial data for which you have non-unique solutions. That includes what we believe are the physical solutions, right? So we believe that there's something like Holder continuous with anomalous dissipation. So what they've shown is that for solutions of that class, there are not unique solutions. But then more than that, I mean, what we see phenomenologically from not only the work that I did, but also, on the shell model with the others, but also work of Guido Buffetta and others who have numerically verified the Kupiainen and Leith predictions for both 2D and 3D Navier-Stokes. So we understand a lot about the growth of unpredictability in turbulent fluids, and it's exactly as Lorenz claimed in his paper. So all of that suggests that this is not an artifact of convex integration. It says that this Nash non-rigidity is presumably something physically real. And it simply means that we have to give up the notion that the solution to the Cauchy initial value problem is a unique solution. In fact, that's probably almost never true in geophysics and astrophysics, especially when turbulence is involved. We have to take the attitude of meteorologists, and we have to give ensemble forecasts. And that's the proper scientific goal. That's the Hadamard well-posed problem, is no longer saying what unique thing happens. When two black holes collide or when neutron stars collide and you want to say, what is the effect on the neutrino emissions? You have to say, no, what is the probability ensemble of things that happened with the neutrino emissions? There isn't one unique prediction. Okay.